Welcome to The Explainer. Today, we're diving into a truly fascinating frontier in artificial intelligence. We are talking about how we're re-engineering AI memory to function a lot more like the human brain. Now, if you've been working with large language models, you already know they are incredibly good at reasoning, but trying to give them a persistent long-term memory that actually works at scale? Yeah, that has been a massive challenge.
It's a pretty relatable question, isn't it? Have you ever noticed how a chatbot or some autonomous agent seems incredibly smart for those first few prompts, but eventually it just starts to hallucinate, repeat itself, or completely forget key details? You might assume it's just hitting a token limit, but the reality of why these systems break down under load goes much, much deeper.
The core of the problem here is a phenomenon known as context poisoning. This is basically when an AI's memory turns against it. Think about it. If an agent makes a mistake and stores it in a standard flat vector database, it's just going to retrieve that exact same mistake later. It reinforces its own errors in this compounding feedback loop. As that database grows, the agent literally poisons its own context window. Okay, let's dive into this. Here is our roadmap for the explainer today. We're going to cover the AI memory crisis, the 4 pillars of memory, hierarchical and graph architectures, how AI agents actually dream, and finally, the art of selective forgetting. Section 1, the AI memory crisis, and specifically when flat vectors fail. When we rely on simple, flat vector storage, which means every memory is treated identically and searched just by fuzzy semantic similarity, we run into 4 catastrophic failure modes. We just talked about context poisoning, but then there's context distraction, which is where the true signal just gets completely buried under thousands of semantically similar but totally irrelevant memories. Then we have context clash. This happens when an agent loads contradictory facts into its prompt at the exact same time, like say an old shipping address and a new one, causing the agent to basically just guess. And finally, work duplication. This is a huge issue in multi-agent systems where agents blindly repeat redundant operations because they don't have shared state awareness. The fundamental problem is clear. Treating all memory as equal simply does not work. Section 2, the 4 pillars of memory, or how we achieve human-like AI cognition. First up, working memory. You can think of this as the AI's active workspace, or its scratchpad. It's restricted by the LLM's context window, and it holds the immediate, real-time conversational context. Just like our own human attention span, it is incredibly fast, but strictly temporary. Once the interaction moves on, this space has to be cleared out for new thoughts. Second is episodic memory. This tracks specific past experiences. It allows the agent to maintain continuity and remember temporal sequences across multiple long-term sessions. So rather than just pulling up random facts, episodic memory tracks what happened, letting an agent actually recall the context of a conversation you had with it yesterday or even a month ago. Third, we have semantic memory. While episodic memory is all about specific events, semantic memory is entirely about persistent facts. This is the agent's core knowledge base. It tracks what is true about the world, about specific domains, or even your user preferences. And it's constantly updating as new, verified information comes in. And finally, perhaps the most powerful part for autonomous agents is procedural memory. This encodes learned skills and validated action sequences. Now, this is the automation engine. And honestly, this is where tool calling happens. Because let's be real, an LLM on its own is basically just a static text generator. Tools are what bridge that text world and the digital world. The agent uses JSON schemas to decide exactly how to execute a real-world action, like is it going to run an API integration, search the web, query a database, or execute some Python code. It stores those successful multi-step actions right here, which means the agent can execute really complex reasoning workflows without having to figure out how to authenticate an API every single time. It's a real game changer. Section 3, hierarchical and graph architectures, and how we actually route this information. The best way to think about this memory OS architecture is that it mirrors a traditional computer operating system. Raw, real-time data enters the short-term memory, or STM. Now, if that data is part of an ongoing topic, it gets grouped and paged into midterm memory, the MTM. But the real magic happens when the system detects high utility, or heat, in a specific segment. Only those highly valuable insights are summarized and permanently pushed into the long-term persona memory, the LPM. So instead of scanning millions of flat vectors, the agent dynamically pages context in and out. That drastically slashes token costs and vastly improves relevance. But what about when facts have to be absolutely exact? This brings us to GraphRAG. Standard vector RAG is fuzzy. It looks for semantic similarity. But imagine you've got a medical agent. Returning a semantically similar drug isn't good enough if there's a lethal interaction with the patient's current medication, right? GraphRAG maps explicit relationships, nodes, and edges, enabling true multi-hop reasoning. The agent traverses the graph to verify facts across multiple connected data points. For high-stakes, verifiable tasks, this is absolutely crucial. Section 4. How AI agents dream, using active dreaming memory. So humans learn from their mistakes by reflecting on them. Well, now AI can too. In the active dreaming pipeline, the agent literally goes into an offline mode. Step 1, a reflector analyzes the root causes of the day's execution failures. Step 2, a dreamer clusters those similar failures together. Step 3, an abstractor formulates candidate rules to solve the problem. And step 4, a verifier creates synthetic scenarios to actually test those rules via code execution. This entire sleep cycle is just brilliant in action. The agent moves from raw episodic traces of failures, processes them through the reflector and dreamer components, and turns them into verified rules that are stored right into semantic memory. During this offline phase, scattered errors like random HTTP timeouts or weird parse errors are grouped together. The agent takes those daily operational failures and turns them into permanent procedural knowledge, applying these newly minted recovery rules in future episodes. Section 5. The art of selective forgetting and the utility of leaving things behind. If an agent remembers every single trivial interaction, every hello and how are you, its database just becomes an unsearchable landfill. To prevent this, architects use the RIF utility formula to strategically prune data. RIF stands for recency, relevance, and frequency. Older memories undergo an exponential decay. Relevance keeps the focus on the current query, but frequency ensures that highly utilized critical memories, even if they are super old, are reinforced and saved from deletion. We are basically applying mathematical biology directly to AI. This is the Ebbinghaus forgetting curve, a core concept from human psychology. To keep agents focused, cost-efficient, and free from context distraction, their memory loss literally has to replicate ours. There's a steep initial decay of raw episodic data, followed by a plateau, where it retains only the most valuable, frequently reinforced information. We have to prune the noise to save the signal. Which leaves us with this final thought. To build an AI that truly remembers everything that matters, we first have to teach it how to forget. As we move away from simple chatbots toward fully autonomous, lifelong learning agents, state management is everything. You have to decide what your agent will hold onto and what it will leave behind. Thank you so much for joining me for this explainer, and I hope this changes how you think about building your next AI system.